Oh, I just realized I wasn't recording. I keep forgetting about recording um, the lecture. So anyway, so I was going over triggers. I'm going to continue with triggers today. So we have, just let me pull up the lecture. Okay, yes. So I'm going to continue with the same example. So in the last class, we had done, for the same example, we did an insert on the employee. Then we did an update of salary on the employee. So these were the two triggers that I did. So I want to continue today. And I'm again going to take an example where I'm going to do an update. But last time I did an update on salary. So this time I'm going to do an update on D number. And so the whole idea out here is that if you make any changes to salary with this D number, it'll affect the total salary here. And if you make any changes to D number too, it would affect the total salary here. So when we, in the last class, when we did an update on salary, the D number was kind of fixed and we were looking at the salary field. And so if you change the salary for the same department, then you have to add in the new salary and subtract the old salary. Okay, so now I'm going to talk about update to D number. So suppose an employee who was in, say, department number 5 switches over to department number 4, then there you have to make two changes. First, one, you have to decrement the total salary in department number 5, which is the old department. And then when he moves to department number 4, you have to increment in department number 4 and decrement in department number 5. So there are two changes in the department table. So I'm going to do the update on department. So that's the next example. So let me just close the one on the left. Okay. Yes. So this is slightly different from the previous example where we updated salary. So first I'm going to do the Oracle version. So after update of D number on employee for each row. Okay, so now because we have to make changes to two different rows of department in this case. So I'm going to write it as so you have multiple, or let me just rephrase this. I have to write multiple SQL statements out here. So because I have multiple SQL statements, I'm going to put it between a begin and an end. So we have begin. And then within that, so then I set total salary. So I increment the total salary in the row where d number is equal to new dot d number, and then minus old dot salary. Okay, and then you put an end. So this is where we finished with the program for this part. So this is an example where when you do a trigger, it is doing multiple SQL statements it's executing. So now I'm going to show how this can be done um, in MySQL, because MySQL has a slightly different syntax, because MySQL, for one, does not really have all the features that Oracle has. And then it has a slightly different syntax anyway. So first in MySQL, the problem is that in MySQL, the moment it sees a semicolon, it treats it like the end of the command. So the moment it sees the semicolon, it starts executing. So that's one of the problems that we have in MySQL, is that how do we deal with the fact that the moment you see a semicolon, MySQL thinks that that's the end of the command and it decides to start executing. And in this case, it'll give you an error because it's looking for an end. So that's the main thing you have to deal with. So when you're doing it in MySQL, the first thing we have to do is to tell MySQL that the delimiter, so this is called the delimiter, that the delimiter has changed. So let's say that we make the new delimiter to be the colon instead of the semicolon. Okay, so then I can start writing the MySQL command. So the first part is just similar to this one, create trigger. So let me just copy this. Okay, so create trigger total salary 3 after update. But again, in MySQL, you can't say off D number. So you just say on employee for each row. Okay, so then let me just start. So now I'll just write it down. So we have begin. So then we have okay, so we have update department, set total salary is equal to total salary plus new dot salary, where D number is equal to new dot D number. And then we have to add on other stuff for MySQL because of the fact that we remove this on D number from the statement. So because of that, we have to add on other stuff. So and old dot D number is not equal to new dot D number. Okay, so then you can put the semicolon out here, and this semicolon now will not create a problem because we have set the delimiter to be colon beforehand. So MySQL is not going to see the semicolon as the end of the SQL command. So then we can do the next part, which is update department. Okay, so this part is similar to oracles, and then we have to add on and not equal to new new dot d number, and then you can again put in the semicolon and it won't create a problem. So that those are the two SQL statements that we have, and then you end. And then you can put the semicolon out here. And again, it's not going to end with the semicolon. So you have to put, so it's the colon that you put out here that shows that this whole statement has ended, and then it'll run. So, so that's the thing in MySQL, is because you have to make sure that, oh, that you change, you add the statement there, because otherwise in MySQL, it always sees the semicolon as the end. And so you won't be able to do this. So this kind of trigger, so like I said, trigger is really powerful. So between a begin and an end, you can put in a whole bunch of SQL statements and it'll run through. So does anyone have any questions? Okay, so just remember that at the end, if you want to go back to using the semicolon, you have to again write this statement delimiter and then put the semicolon. So then the semicolon will come back to becoming the statement that will end a SQL command. Okay, so so I do want to say that triggers, like I mentioned, they are a lot more powerful than constraints. So you can have a trigger can set off a chain of triggers. So let's say that we have this trigger called total salary. We have implemented, and I mean, we have written this total salary and it's saved as part of your DDL. All of this is part of the database schema. So suppose I add on another trigger. So let me call this, so I want to show how you can get a chain of triggers. Okay, so we have okay, so this trigger is on after an update on the department table. That is the second table out here. So this trigger is going to get activated when you update the department table. So update. So once you update department, you should update department location. So set d location is equal to maxed where d number is equal to d number, and a new dot total salary. Okay, so this trigger chain one is on the department location. When department is updated, it will go and update department location. So suppose I type in this command, update employee, set d number is equal to 1, where social security number is equal to 1234. Okay, so here I'm updating the employee table. So when I update the employee table, since I have this, all these triggers that are set up on the employee table, when I update the employee table, the triggers that will update the department table go off. And when you update the department table, then it'll update this particular table. I mean, this particular trigger. So making a change to employee triggers off changes to the department. Making changes to department triggers off changes to department location. And then if you had some other trigger where if you change department location, it triggers a change in, let's say, the project. So all of them, it will start cascading down. So that's why I said it's a trigger chain. So so therefore, triggers are, they can affect all the tables in a database, depending on how it goes. So um, yeah, so that's it about triggers in general. If you want to see all the triggers that are there in your database, you can use this command, show triggers, and it'll show all the triggers that are there. I don't think that by default there are any triggers on your company database. I don't recall putting anything in there. So if you write down some triggers and put it there, you'll see all those triggers. If you want to drop a trigger, you can give the command drop trigger. And let's say you want to remove chain one, you can just say drop trigger chain one. So in general, like I said, I don't think that MySQL's triggers are as powerful as the triggers in other databases. So MySQL, like I mentioned in the last class, it does not support multiple triggers on the same table. So MySQL does not support multiple triggers with the same action time and event on the same table. I know that doesn't make that much sense. So what I mean is, let's say that um, you have a trigger on the employee table, and the trigger on the employee table affects the department table. And let's say that the trigger on the department table affects the department location table. And then the trigger on the department location table goes back and affects the employee table. Now that is not permitted in MySQL. It is permitted in many other databases, but not in MySQL. So you cannot have the same, you can't circle back to the same table. Or like the example I had in the last class, let's see, the very last one where I was trying to show an example of where I had these triggers, limit one and limit two, where you were updating employee and the trigger was on employee itself. That's not allowed. So you can never go back to the same table. So this is just a limitation of MySQL. And so on a table, in a database, there are all these kind of triggers. You have you have primary key constraints, you have the foreign keys, then you have these triggers. But in the order in which they are run, triggers have a lower priority, so they are run after constraints. So So if you have some foreign key and primary key kind of constraints in your database, those are run first and then the triggers are activated after that. So do you have any questions on the, on triggers? Because I'm pretty much done with triggers with this. Okay, I noticed that more people have signed to come on to the lecture right now. So I started with the quiz. So I just want to, before I go on to the next topic, I just want to put up the quiz solution again, because I think there were very few people when I was showing the quiz. So if you have any questions on the quiz, just go ahead and ask me, because on the final exam, now I just realized we just 2 weeks, we just have 2 more weeks of lectures left. So on the final exam, most of the questions are going to be based on the second half of the semester. Um, which is really, we started up with design. So the majority of questions are from the second half. There are going to be very few questions from the first part, which is relational algebra and SQL. I haven't set up the final exam yet, but I already know that, that I'm not going to give very many questions from that end, because you had a lot of assignments where we tested all that, and it's been a while. I'm sure a lot of that stuff is mapped out of your head anyway. So, so if you have any questions on the quiz, just go ahead and ask me. Okay, if not, I'm going to just continue. Okay, so the next topic I'm going to talk about are indexes. So the reason you get such great performance from your database is because you have indexes in there. If you didn't have indexes, your database would be very, very slow. And as you can guess, these indexes are there on every primary key. Definitely, you have indexes on primary keys. Um, and you haven't got to this class without having done data structures. So everyone out here would know what indexes are. So I'm not going to explain what indexes are out here, because, nor am I going to explain the data structures that are used for indexes, because those are things you should have got from either the data structures class or algorithms class, because the common indexes, I mean, there could be any kind of data structures, but the most common indexes on are hash indexes or B tree indexes. And I know you do hashes in data structures. Do you do B trees also in data structures? Anyone just answer yes, no?
We did, I think, but it's really brief. So probably like I don't remember them very well, at least.
Okay, so you don't remember them that much. So that's the thing, it's beyond the scope of this database class for me to go into B trees, but I will, when I explain B trees, I'll kind of show it. So it should come back. I mean, I'm not going to ask you how to insert into B trees or delete or evaluate that, their complexity of insertion, deletion, or update or anything like that. So you would do B trees in the algorithms class in a lot more detail. I'm almost certain of that. If you don't do it in data structures, definitely it has to come into algorithms, because it is a very, very important data structure. So the most common indexes are done using either hashes or balanced B trees. But as you, there are other data structures that are very good for, because there are inverted indexes, there are all kinds of data structures. A lot of the stuff you do in algorithms, many of those data structures are used for indexes. So the textbook actually does go into a lot of detail of these index data structures, but I'm not going to do it here. It's because it's like going back to a data structures or an algorithm class. So I think it's not the scope of this class. But what I want to teach you in this class is, um, you know, how indexes what indexes are useful and what indexes are not useful. If you were designing a database, what are the indexes you would want to put on the database? So things like that. And as long as you have an idea of what the underlying is, that's sufficient. And if you want to know more details about those data structures, please take algorithms, which I think is a required class right now for undergrads and for grad students, which is good. I have to say that, um, you know, so I did, once you specialize in an area, your work tends to be in that area. So my work is in either databases or systems. But outside those two areas, the one topic is that I have to constantly kind of use and keep it in my, you know, kind of know about is algorithms. I think that is kind of really important. Um, that is really important class, because you can map out a lot of stuff. Once you start working, a lot of the stuff that is going to get mapped out. If you don't use it, you kind of, not going to retain it. Things like compilers and all, I barely remember those things. I mean, I did those things years ago, but I don't really use, that kind of knowledge all the time. Um, but think algorithms, I do have to kind of know it. And of course data structures is very fundamental, so you kind of have to use that. But yeah, so it's a good idea to I mean, now it's required, so it's not something this it's not like you have a choice to it, but I would just always recommend algorithms. It's an important class. Okay, so now coming back to indexes. So in your database, all the tables that you have, they are stored on disk. So but indexes are also, they are data structures that are also stored. So before I write down, I just want you to know this, is that all these tables that I spoke about, all of them are stored on the disk. But that is not the only thing that's stored on the disk. With every table that you store, there are indexes also that are stored on the disk. So, and a very common index, I mean, in fact, is the primary key index. So for, let's say, the employee table, which has a primary key is social security number. So an index of social security number, which, since all of you know what hashes are, let's say it's a hash index, that will also be stored. It's a file, it's persistent. That index is also stored on the disk along with your employee table. And the reason for that is, let's say that I want to search. So I have a SQL query saying select, um, select that row, select star, where social security number is equal to 1234. So let's say employee table has 10,000 rows. And if I said that I want to select the row with social security number 1234, then you'd have to upload 10,000 rows from the hard disk, and you have to go through. I mean, in the worst case, maybe out of 10,000 rows, maybe your social security number is the very last row. So you have to upload all this data and search through 10,000 rows. Now, since everyone who's taking this class has taken operating systems, you know how much time it takes. If you go down to the disk is the big bottleneck, where your CPU is working in microseconds, and your main memory, everything is working in microseconds. When you go down to the disk, you're working in milliseconds. It's so much slower, order of magnitude slower. So it would take so much time. This database wouldn't work at all, because just a simple query like select, the row with social security number 1234 would take forever to do. So because of that, what happens is that you have indexes. Also, files are huge. So, 10,000 is small, but files are terabytes long. Your main memory is small. So this is all your operating systems knowledge. You know that main memory is small. You can't load the entire um, file into main memory. It may not fit in main memory. So then it's another big hassle because you have to load parts of the file, search, put it back. All of this is very slow. On the other hand, if you build an index, on the social security number, indexes are tiny. I mean, if your file is terabytes long, an index might only be kilobytes long. So you can upload the index into main memory quickly. And really, what is an index? An index is, so it'll have the social security number. So let's say the index is on social security number. So when you pull up an index, all it has is the social security number and a pointer to where that particular row is stored on the disk. So you can load the entire index into the main memory, search it, and then you can go down to disk and bring up the row. So that's so much faster. All you have to do is load the index, which is tiny. So you have 2 accesses to disk at the most, where in the other case, you would have to have so many accesses to the disk to search. It's easy for you to relate. When you look in a textbook, for example, any book, the last few pages. So if your book is, say, 1,000 pages long or 500 pages long, an index might be only 2 or 3 pages long. But whenever you look up any topic, it tells you which page to go to. So you look to 2 or 3 pages, which is in sorted order. So let's say I want to search for bee trees. Can go down to the index, which is 3 pages long. I look for it's an alphabetical order, so I don't even really have to search it. I can just go to the B part, look up bee trees. It'll tell me which page it is on the book. So it's so much faster. So that's the same idea with databases. That you have these indexes, and without these indexes, you wouldn't have databases. So let me just summarize what I just said. It's just I did say a lot. So. But I hope you got the idea of indexes. Even if you didn't know it, I mean, I think you would have known it by the time, but even if you didn't know it, you understand what it is. So, and but you shouldn't feel bad if you've forgotten stuff, that you did earlier. You're bound to forget. It's just, I don't remember. The only things I remember are the things that I keep doing. You don't really remember stuff that you did in the old days, but you still, if you have never done something before, then it's a lot harder to figure out. Even if you've done it and studied it, you've forgotten it now, but it'll come back to you, and you still are, you'll kind of understand what's going on, and you're more receptive to it. So it's okay, because if you, I mean, it's not okay. You will forget. It's not a matter of okay. Our human brain can only retain so much at a time. So you're bound to forget a lot of stuff that you learned in the past, but the memory of it is always there. So when you see it later, at least you'll know you've done it before, and easier to figure it out. So they're hash indexes and they're balanced B trees. These are the most common indexes in relational databases. So this one is an order of log n. Let me just call it log n. So an index is also a file that is part of the database. And the indexes are stored along with the files. And so, like I mentioned before, why do we have indexes? Reasons. So files are very large. So 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 because files are large, the storage access time. The storage access time is very high, and the entire file may not fit in main memory. So because indexes are so much smaller um, than files, so because of that, you know, um, you can store the entire index into main memory. So let's trying to see. Okay, so that's the way that in a database. Let me give you an example. So if you have, so suppose you have a table R, and then with the table R, at the minimum, there will be at least one index file, and that would be the primary key index file. So you have a table R, and then you have an index file. So let's say on attribute A, so attribute A uh, is usually the primary key. I mean, it is always the primary key. There's always by default an index on the primary key. So is a primary key, and the index is built on this. So on the primary key. So the index file A, so is very much smaller than the size of R. So if it's a hash index, and like I said, you know, it could be either a hash or a B tree index. I think in MySQL by default it's B tree indexes. I think, I'm not completely certain. But if you want to have it as a hash, you can just specify it. But I think the default is B trees. So if you have a hash index, so suppose it's a hash index, then you would say that R dot A is equal to X. Because for hash, what you say, you know, that's how you search for hashes. You look for something. So if you say employee number is equal to 1234, and you can go and find, you know, where 1234 is stored. But B trees, and if you don't, I know you said you don't remember B trees, so I'm just going to go briefly on B trees. So B trees, you're really looking within a range of values. So for example, you would do X less than R dot A less than Y. So we would do, so you're looking like, you know, salary between 20,000 and 40,000 is, that's a good one for a B tree index. So if you drew this, let me see. So let's suppose you have this range of values, 20, 40, and 60. So I'm trying to kind of explain B trees in a non-formal manner. So informal. Okay, so and then we have, Okay. So you have a range of values like this, and then let's see from 20. And then you have pointers to where these things are stored on disk. So we have, okay, so this is a rough image of what a B tree looks like. Um, it's so you have values. So let's say that someone says that search for um, so the search for departments, say twin search for departments that lie that are greater than 20 and less than 40, let's say. So or less than 35, or 32, let's say, departments that are greater than 20 and less than 32. So then you look, so this is a B tree. So you have some values 20, 40, and 60. So the first pointer points to all the locations that are less than or equal to 20. The next one then out here, it points to locations that are less than or equal to 40, or less than 40. Then this one points to less than 60. And then the last one is pointing to greater than 60. So if I had a query that is searching for departments between, say, 25 and 35, I would use this pointer. So I would have to pull up, if it's a B tree index, I would go from there, and then I would go and pull this up. And then this points to all the disk locations where all these departments are stored. So then you can upload it from that. So does that make sense? Do you have any questions? So, I mean, this is a very rough idea. And again, I am kind of assuming that you have done something in B trees, even if you don't remember, something along this lines in data structures. So, and even if you haven't done it, I just want to, all you have to understand for the database class is that there are data structures that store some primary key or a candidate key. It stores some attribute and it tells you where the corresponding tuples are stored on disk. So if you have a search or based on that particular attribute, so for example, if you have a search on social security number, all you have to do is pull up the index, and the index is so much smaller. So you can search through the index. And once you find the corresponding value in the index, say social security number 1234, then all you have to do is go to the pointer and you can find it on disk. So that's the basic idea of an index. So even if you don't understand a B tree or a hash, as long as you understand what an index is, that's sufficient. So there are different types of indexes. So there are primary key indexes. Every table will have a primary key index. Then you have clustering indexes. Then you have secondary indexes. And then you have multiple attribute indexes. And I'll just talk about these. Okay, so primary key is the easiest one since, like I mentioned, that there are um, indexes always on the primary key. Okay, so the thing with the primary key indexes are very often your table may be stored in a sorted order by the primary key, because it's much easier to search a sorted table than an unsorted table. So normally databases are sorted. I'm not normally most tables of a databases are sorted by primary key. So, and if the table is sorted by this key, then the indexes can be sparse, and I'll kind of explain what that means. So then you have a sparse index. Okay, so let's say this is a disk block. So you have disk block 1, disk block 2, and so on. And let's suppose it is sorted on the primary key. So let's say the primary key. So we have, let's say 1, 2, 3, 4, and so on to 10, 11, 12, 13, and so on to 20, and so on. So then in this case, all the index needs to do is point to the first. It doesn't have to point to 2, 3, 4, 5, 6. It just needs to point to the first um, number on each block. So you don't need to have to point to every single primary key tuple location does not have to be pointed. You can just point to the very first one. So in this case, you don't have to keep an index on every single element. So that's called a sparse index. And I'll continue with this in the next class unless you have any questions.